So, hello everyone. I'm Gouthami. I'm a student studying in third year of Information Science and Engineering in Sapthagiri College of Engineering. So today we're going to be discussing about trees. That is a module. This is the module 4 in data structures. So let's discuss the topics that we're going to discuss about. Is gonna consist of introduction to trees, then binary trees and its properties, then types of binary trees, binary tree representation, and binary tree traversals. So let's get into what is trees, what are trees. So how do we uh, introduce trees and its properties? So what is a tree? So let's define it. So a tree is a set of finite set of one or more nodes that shows parent-child relation, such that there's a special node called root node. All right, and then the remaining nodes are partitioned into disjoint subsets, that is T1, T2, T3, and so on till Tn, such that the n should be greater than or equal to 0. All right, so which all the children of root nodes are themselves are called to be subtrees. So let's see this diagram and it'll be really easy to understand. Let's see here. So this tree has totally 1 2 1 2 3 4 5 6 7 8 9 10 nodes, right? Here, sorry, here. So there are totally 10 nodes, and of which A is called the root node and other nodes are called the children nodes. Here B and C are the child nodes of A. So there'll be two subtrees, subtree B and subtree C. So here there'll be three subtrees identified. So the node A is the parent of B and C, and here D and E are the child nodes of B, F and G are the child nodes of C, H and I is the child node of D, and J is the child node of E, right? So each node which does not consist of any child nodes, the end nodes of a tree are called as leaf nodes, and each tree has levels. So the root node is at level 0, and here in the second level, then this is called as level 1, then level 2, level 3, and so on. So after finding the level, so you find out the maximum height of the tree. How is height measured? Height is measured by number of levels plus 1. So in this case, there are 3 levels. So it will be, height will be, or depth of the tree is measured as level plus 1, that is 3 plus 1, and it will be 4. So the height of this tree is 4, right? So next, let's discuss about binary trees and its properties. So what are binary trees? So binary tree is a tree which has finite set of nodes that is either empty or consists of a root node and two subtrees called left subtree and right subtree. Okay, it can be partitioned into 3 subgroups, namely the root node, the left subtree, and right subtree. So what is for the root? The root, if the tree is not empty, the first node in the tree is called the root node. Then left subtree. It is a tree which is connected to the left side of the root node. Since the tree comes towards the left of the root, it is called the left subtree. Right subtree, it is which connected to the right side of the root node. Since the tree comes towards the right, it is called the right subtree. That's it, right? So next, let's come to the properties of binary trees. So there are two main properties, which is lemma 1 and lemma 2. The lemma 1 states that the maximum number of nodes on level I of a binary tree will be equal to 2 power I for I greater than or equal to 0. And the maximum number of nodes in a binary tree of depth k will be equal to 2 power k minus 1. So let's get to the proof and we'll see how it works. So consider the following complete binary tree and observe the following factors from the complete binary tree, right? So here there are 3 levels in the diagram. The following tree representation, there are 3 levels and the depth will be 4 as we've calculated, that is the height of the tree. So let's see how the number of nodes at each level. So here number of nodes at level 1, level 0 is 1, that is a root node, and number of nodes at level 1 is 2. Number of nodes at level 2 is 4, and number of nodes at level 3 is 8. So basically we can represent this in terms of 2 power I, that is 1 can be represented as 2 power 0, 2 can be represented as 2 power 1, 4 can be represented as 2 square, and 8 can be represented as 2 cube, and so on. And number of nodes at level I will be 2 power I. So total number of nodes in the full binary tree of level I will be the sum of all of these. So it will be I equals 2 power 0, 2 power 1, 2 power 2, and so on till 2 power I. So this series is in terms of geometric progression whose sum is given by S is equal to A into r power n minus 1 divided by r minus 1. So where A here is 1 and n. So n is actually called as the height of the tree. Height of the tree is represented by n. So what is the formula for height? It is number of levels plus 1, where number of levels here is I. It will be I plus 1 and r will be 2. Right? So we'll substitute in this equation. So that will be A is equal to r power n minus 1 by r minus 1. That is A here is 1, r is 2, and n is given by I plus 1 minus 1 divided by r is 2. That will be 2 minus 1. So substituting the equation, you will get 2 power I plus 1 minus 1. So this will be the total number of nodes, where nt will be 2 power I plus 1 minus 1. So for the above tree, the level is 3, right? So let's substitute I to be 3 and let's see. So we get, substituting I as 3, that is 2 power I, that is 3 plus 1 will be 4 minus 1. So 2 power 4 will be 16, 16 minus 1 will be 15. So which is the total number of nodes in a fully binary tree. The depth is measured by maximum level plus 1. The level is 3, 3 plus 1, that is I plus 1, right? So substituting the value in the above equation, we get I plus 1 to be k. So 2 power k minus 1, hence proved. Right? So let's go to the second property, which is the number of leaf nodes is equal to number of nodes of degree 2. Right? Consider a binary tree of degree 2 nodes. That is, each node in the tree should have maximum of 2 children. A node need not have any children, so or it can have only 1 child, or it can have 2 children, but a node cannot have more than 2 children. That is degree 2. Degree 1 means a parent node can just have a child, 1 child node. Degree 2 means a parent can have either no child nodes, 1 child, or 2 child nodes. It cannot have more than 2. Degree 3 means it can have maximum of 3 child nodes. So here, so this it states that the number of leaf nodes is equal to number of nodes of degree 2. So it will be, it can have not have more than 2 children. So it will be, it's just 2. So let number of nodes of degree 0 will be n naught. Number of nodes of degree 1 will be n1. Number of nodes of degree 2 will be n2. So the total number of nodes will be addition of these. So it will be n0, n1, n2. And let's consider this to be as equation 1. So observe from the tree that total number of nodes is equal to the total number of branches, that is b plus 1. So n will be b, that is total number of branches, plus 1. Let's take this as equation 2. If there is a node with degree 1, number of branches will be 1. That is only one child node, right? Degree 1 means one child node. So number of branches will be 1. So the number of nodes of degree 1, number of branches will be n1. Let's consider this to be as equation number 3. With degree 2, branches will be 2. So for degree 2, number of branches will be 2n2, because there are two branches, right? So it will be 2n2. Let's consider this as equation 4. So by adding equation 3 and equation 4, we'll get b, the total number of branches will be b is equal to n1 plus 2n2, right? So let's substitute. We know that b is n is equal to b plus 1, right? So let's substitute this. So this will be n is equal to n1 plus 2n2 plus 1. We'll substitute this equation in equation number 2. Here n is equal to, what is b? B is n1 plus 2n2 plus 1. That's what we've got in equation 6. The relation between number of leaf nodes and number of nodes of degree 2 can be obtained by subtracting equation 6 by equation 1, because there are 3 degrees here. Let's subtract. So n, let's change the signs change. So n will get cancelled. So n1 minus n1 will get cancelled. N2 minus 2n2 will be minus n2, n0 will remain the same, and plus 1 will be minus 1. So this will be n0 is equal to n2 plus n1. So by rearranging, we get to this equation.